This is the lecture for Wednesday, March 11th. We will be continuing our discussion of the weak interactions. So let's take a look at beta decay. So the beta decay can describe the decay of a neutron in vacuum, where the neutron decays into a proton and an electron and an anti-electron neutrino. That's what's shown here. Now it can also occur inside of a nucleus. Fermi's description of this interaction, it's not the complete picture of what's going on, but the way Fermi thought of it was you have this interaction, some sort of like a vertex, point-like vertex involving the neutron coming in, proton going out, an electron going out, as well as a anti-electron neutrino. So that's what's encoded in this interaction here. And then there's this coupling, G, which is what's called Fermi's constant. Now, we know now that this point-like interaction is really not a point, but rather this is mediated by a W minus particle, as well as the W plus in other instances, as well as the Z0. We'll talk more about that here. Now, we not only have the possibility that the neutron can decay into a proton, electron, anti-electron neutrino, but if it's energetically allowed, the proton can decay into a neutron, positron, and an electron neutrino. However, in vacuum, the proton can't do this because the right-hand side has more energy than the original. Take a look at the proton mass. It's 938.27, whereas the neutron is 939.57 megaelectron volts. But if the proton inside of the nucleus, if you consider the binding energies, if the conversion of the proton to the neutron will release some energy, will lower the binding energy, will lower the energy or increase the binding, then this may be energetically allowed. Now there are some other decays that we should talk about. Now the word lepton refers to muons, electrons, and neutrinos. So when we say semi-electronic, that means part of the process involves electrons. Half of the process, half of the process involves leptons. Okay, so but let me tell you more about these pions. So let's, for example, take a look at pi minus. Pi minus, at the simplest level, you can think of it as having an anti-up quark and a down quark. And so the process in which the pion, let's say the pi minus decays, you have a pi minus, so you have an anti-up quark and a down quark coming in. And then this produces a W minus particle. And then this W minus particle then produces either electron or a muon. It's a muon here. And a muon muon neutrino. So that's this decay here. And you can also produce an electron and anti-electron neutrino. Now you can also have a purely electronic process where it's all only involving electrons. And so in that case you have a diagram that looks something like this. We have a muon coming in, and then we have the muon neutrino, and then we have again the W minus, and then we have the electron and the anti-electron neutrino. And that's the decay of the muon. Now, I mentioned this Fermi coupling constant, G Fermi, and it has a numerically small value when measured in typical energy units for things involving the strong interactions. And the reason why this is a very small coupling constant is because this particle, this W particle, or the Z particle, they have very large masses compared to that of the proton and neutron. So this is about 1000 MeV is 1 GeV, so this is approximately equal to 1 GeV for the proton or for the neutron. And however, these the W boson, the Z boson, have either 80 times that mass or about 90 times that mass. So you can see, and so as a result, there's a suppression by 1 over the mass squared of the particle. And because it's a very heavy particle, this process is very weak. Hence the word weak interactions. Now, another consequence of the fact that it's a very heavy particle is that the uncertainty principle requires that this virtual particle cannot exist for very long. It can't travel very far, and so as a result, this essentially looks like a point-like interaction because this distance is inversely proportional to the mass of the particle. If you want something on the order of 10 to the minus 3 femtometers, where femtometers is the typical scale for things involving strong interactions, like the size of the proton. Okay, so let's take a look at some different beta decay processes and the energies involved. So we're going to use some notation here. For the atomic mass, the rest mass will be mc squared, or atomic, actually the rest energy of that corresponds with the atomic mass will be mc squared. Okay, and m itself will be the atomic mass. And this n prime, sorry that the prime here is a little small to see, that will be the nuclear mass, so m prime c squared. And then me will be the mass of the electron, so if we have z electrons, then the rest energy will be z me squared. And then we will subtract off the electronic binding energy. So then we have the result that the atomic mass, the rest energy corresponding with the atomic mass, mc squared is equal to m prime c squared from the nuclear mass, plus the rest masses of the electrons minus the binding energy, electronic binding energy. Okay, so now we can take a look at the energies involved in beta decay. So in beta decay we have A nucleons in total, we have Z protons and N neutrons. In beta decay, one of these neutrons converts into a proton, that's why Z goes to Z plus 1, and the number of neutrons goes to N minus 1. Alright, and we also get in beta decay an electron and an anti-electron neutrino. Now, the Q value is the difference between the rest energies on the left side minus the rest energies on the right side. The rest energy for the neutrino essentially has very, very small mass, so we can neglect that compared to everything else. And so now, if I want to try to calculate what the Q value of this process is, well, I can simply calculate this in terms of the rest energy for the parent nucleus, for the parent nucleus here, minus the rest energy for the daughter nucleus here, okay, minus the rest energy for the electron, and we neglect the rest energy for the neutrino. Now, I can massage this a little bit by noticing that when we talk about atomic masses, we're always making the number of electrons equal to the number of protons to find the mass of the that's suggested here. We always make the number of electrons equal to the number of protons, so that the atom is neutral. So if I were to replace these nuclear masses by atomic masses, then I could actually suck up the fact that there's an extra electron here, because the Z plus 1 will then get me one more electron. So that's what I can do here. I can write the Q value of mp(c) squared minus md(c) squared. Okay. Now you may complain because I didn't take along the the binding energy for electronic binding energy, but this correction will be relatively small. The change will be quite small, so that's not something I'm going to worry about at this stage. Approximately true to calculate the Q value this way for beta decay. Now we can also take a look at beta plus decay, where the proton now will decrease by one. Will remove one proton and will increase the neutron by one, and then get a positron and a electron neutrino. Now in this case, once again, we can measure the Q value, the difference in the rest energies on the left side minus the rest energies on the right side. So we have the rest energy for the parent nucleus minus the rest energy for the daughter nucleus minus the rest energy for the positron, which is the same as the rest energy for an electron. Okay, now we can do the same game here, but the difference is that for the daughter nucleus we have Z minus 1, so we have one fewer electrons. So if we were to try to do the same game here, we will see that we actually end up getting a plus 2 times the rest energy of the electron. So if we compare then the masses of neutral atoms for the parent and the daughter, then we actually need the parent to be more, it needs to be 2 times the rest energy of an electron plus the rest energy of the daughter nucleus. So there's an extra 2 MeC squared that you have to be above before it can decay through this channel. Okay. Now, the electron capture is another process. Turns out to be very similar to, well, let me make this comment after I discuss the process, and I'll show you why this is actually somewhat similar to the beta plus decay. Okay, so in electron capture, what happens is that you have essentially a proton. Proton combines with an electron and becomes a neutron with a electron neutrino. Okay, so the atomic electron is captured by a proton, and so as a result, so that's what's shown here. This electron gets captured in the K shell, so that's the lowest lying shell, n equals 1. And so then now the electron is gone because we've converted one of the protons to a neutron, but the electron is gone. Now then what will happen though is the atom is in some excited state, and you can then de-excite this atom by either emitting a photon, a gamma ray photon, or you can actually have the this excited electron falls down and emits a photon, or we can have actually this guy can fall down, and instead of emitting a photon, we can actually release the extra energy by kicking off a outer electron with the kinetic energy that the difference between the final and the initial kinetic energy bounces off the energy of this drop down from the excited state down to this hole here. Now, so here's an example where we have carbon 11 with 6 protons and 5 neutrons. It captures an electron in let's say, the K shell, and then it converts into boron, which has 5 protons, 6 neutrons, but then you get an electron, a neutrino out of it. Okay. Now, so this diagram here, this is sort of the generic beta decay diagram, but we can draw it in various different ways. So let me do that now. So if I think of time as flowing upwards like this in my diagrams, I'm going to draw these timing diagrams. So the simple standard beta minus, the beta decay, that's when the neutron comes in, proton is one of the outgoing particles, we have a W minus, and then we have electron, and we have the anti-electron neutrino. Alright? For the beta plus decay, we have instead of proton coming in, and then we have a neutron going out, and then we have a W plus particle that's produced, and then we have a positron, and we have an electron neutrino. Now, the electron capture diagram is actually very similar to that. We have a proton, we have a neutron going out, proton coming in, neutron going out, we have a W plus, but the difference is that we have, in this case, we have the, sorry, we didn't mean to draw that here. We have the neutrino, but the electron is actually going to be coming in. So instead of having a positron going out, this line is sort of bent backwards in time. And so we have the electron coming in, and so we have the proton and the electron coming in, we have the neutron and the electron neutrino going out. So this is an example of what's called a crossing diagram, where you flip one of these lines so that it goes from an outgoing particle to an incoming particle, and they are actually related to each other they're actually the same amplitude, it turns out. The strength of this diagram, this process is exactly the same. Okay. Now, while I'm drawing all these Feynman diagrams, I should mention something we'll talk about later, but it's maybe useful to talk about now. So neutron, in terms of the quark level, is up, down, down. So an up quark, a down quark, and down quark at the simplest level. And the proton is an up quark, and up quark, down quark. It's not really that simple. We'll talk about quantum chromodynamics later in this class. And there's actually a whole bunch of diagrams that complicates this picture, but at the very simplest level, you can think about sort of a toy model of the neutron is an up quark and two down quarks, and the proton is two up quarks and one down quark. So in that way of thinking of things, then this beta decay diagram can be thought of like this. We have these three quarks, okay, and we have, let's say, this guy's a down, down, up, up, and then this one here is a down that gets converted to an up, and it spits off a W minus particle, and then we have the electron and the anti-electron neutrino. Alright, so that's the neutron converting into a proton. That's what beta decay really is in the quark language. Alright. By the way, if you have any questions, please, when you do your summaries, you can go ahead and well, so separate it from your summary, but ask your question in the email reply with your summary. Okay, so here are some examples of beta minus decay. Okay, so we have beta minus decay involving neon 23. Okay, and going to sodium 23, involving a Q value of 4.38, and the lifetime is 38 seconds. Okay, a few other beta decays. There's another beta decay with a much longer lifetime. And then here is now a beta plus decay, where we have positrons and electron neutrinos, involving aluminum 25 to magnesium 25. Right, and then we have electron capture, where we have oxygen 15 going to nitrogen 15. And so you can sort of visualize this in terms of energies. So this is kind of drawn in a funny way, but this is just measuring different energies. So you have various energy levels, and the difference between the atomic energy for Z protons, Z plus 1 protons, or Z plus 2 protons. So when we do a beta minus decay, it's going from this state to this state here, all right? We're increasing the number of protons by 1, we're decreasing the number of neutrons by 1, and the energy difference is this gap in the energies. When we do electron capture, what we're doing is we're getting this difference between these two guys here, all right? Now the now for beta plus decay, we have this Okay, this is a little bit confusing how we put all these two together. So then there's a gap of two mass of the electron c squared between these guys here, and this separation energy is the Q value for beta plus, and this guy is the Q value for the electron capture. Okay, and the electron capture, you can pay attention to the various different electron orbitals in which you're capturing from, and that will make some small difference to the energy release. Now, the next thing we'll talk about is a very interesting application. So radiocarbon dating. So carbon-14 will decay by beta decay to nitrogen-14. It has a very large half-life. In fact, this is one of the mysteries of nuclear structure theory, that it's not really clear why it has such a large half-life. If you were to just do a simple calculation from a shell model or some ab initio calculation, you would estimate that the half-life would be many orders of magnitude smaller. There's something unusual that makes it such a long-lived nucleus, but that's to be discovered later. Now, radiocarbon dating actually takes advantage of the fact that carbon-14 is produced in the atmosphere by cosmic rays striking the atmosphere and producing these carbon-14 isotopes. They decay though, and so there's some sort of equilibrium that then exists in our atmosphere, in the air. Now, so this is then this carbon-14 chemically looks the same as carbon-12, and therefore it makes molecular compounds. It makes compounds like CO2 that's absorbed by the trees, plants, and it's used it's absorbed into the organic material of the plants. Then it gets into animals and everything that's living. Now, but then when an animal or a plant dies, then this respiration process, this intake of carbon-14 stops, and because it has a half-life of 5,730 years, very slowly the carbon-14 then starts leaving. It gets converted to nitrogen-14. And so if you measure the relative, now there's nothing really happens to the carbon-12 because it's perfectly stable. So if you can measure the relative abundance of carbon-14 to carbon-12, you get some estimate of when the living object stopped exchanging carbon with the environment. And so then you can figure out when something died, or for example, the level of carbon-14 in plants and animals when they die. That gives you some measure of the carbon-14 in the atmosphere at that time, okay? And also how long ago it died. Now, you can also do carbon dating, the extension of carbon dating using other isotopes. So you can use, for example, krypton. You can use argon, carbon. Well, we were talking about carbon. Different isotopes of krypton. Krypton 85, krypton 81. So krypton 81 has a much longer half-life, and so that can be used for really old objects. For example, you can measure water aquifers, sort of groundwater storages, to see how long they've existed by measuring the krypton 81 abundances. Right? And that's what was done in some very interesting research involving aquifers in Brazil. Okay, now let's talk a little bit about neutron beta decays. This is just neutrons in vacuum. So you think this would be something we would completely know and understand now, but there's actually an interesting puzzle that still exists. So astrophysicists rely on knowing this free neutron lifetime to be able to get a model of nucleosynthesis, the production of elements starting from the Big Bang. And it's also related to fundamental parameters of the Standard Model. However, when we do very careful measurements of the lifetime of the neutron, we don't yet get a fully consistent answer. There's discrepancies at the level of about 1%. So the NIST value, the standard sort of value, is that the lifetime is 887.7 seconds, about 14 and a half or so minutes. Now, however, there's two different ways of making this experiment, of doing this experiment to measure the neutron lifetime. And there is what's called a beam experiment, and then there is a bottle experiment. So a beam experiment is when we have a beam of neutrons, and the neutrons decay into protons, and you detect the protons, and that detection of the protons then tells you the rate of beta decay, and then you can deduce the neutron lifetime if you know something about the flux, the original flux. Now, you can also do a bottle experiment where you trap some neutrons and you sit there for a while, and then in this trap, and then you measure how many neutrons you have left. The assumption is when it decays, it leaves the bottle, and it gets kicked out of this cold bottle. And so you count the number of remaining neutrons, and that tells you how many decayed. Now, so what's puzzling is that these don't agree with each other as of now, although the beam results seem to have rather large error bars, so you can imagine maybe that's not really precisely determined yet. But the bottle result seems to be stabilizing, well, to some value like 880, whereas the beam results are more 888. Now, there have been some papers which suggest maybe they are different, which would kind of be exciting, but also maybe quite unlikely, that there might be physics beyond the standard model of particle physics, that the neutrons actually decay into something other than protons, electrons, and anti-electron neutrinos. If that were the case, that could describe what's going on here, because if you measure the beam, if you do the beam experiments, you don't see quite enough protons, which is the reason why the half-life, the lifetime is a little bit bigger, whereas for the bottle, you see all of the decays because you're just measuring how many neutrons are left, and so as a result, you get the smaller lifetime. Let's see. Okay, now let's talk about the beta decay rate. Okay, this is just following the Fermi's golden rule, which we've talked about. So last time we wrote this as the density of states for a given energy, but the density of states is just the number per delta E, or dE, the number of states per delta per dE. So the Fermi golden rule is that the rate is 2 pi over h bar, the absolute value squared of the amplitude. Okay, this is the initial state, and this is the final state, and this is the interaction that drives the decay. There's an assumption that it's a very weak process. It's a weakly interacting process. Okay. Now, so we have then the original nucleus. So let's say we're in the rest frame, and so the spatial momentum of the parent nucleus is 0. So as a result, the sum of the momenta of the daughter nucleus of the neutrino and the electron should add up to 0. That's what we have here. We also have energy conservation, that the kinetic energy of the deuteron, not the D is for the daughter, plus the kinetic energy of the electron, plus the kinetic energy of the neutrino. So this is the kinetic energy added together is equal to the Q value. That's the differences in the rest energy. So these E's stand for the total energies of these particles, but these T's stand for the the kinetic energies. Okay. Now, I'm not going to go through the derivation of the phase, this phase space vector here. This actually requires doing some integrals over various spherical shells and such, but it's not too hard, but it's not really exactly what I want to spend your time in this class doing at this stage. But what you end up getting is the momentum of the electron squared here, okay? And then you have then for a given energy minus the energy of the electron squared. So and we also have the this energy difference in the denominator with the mass of the neutrino squared here. We'll talk about this in a moment later. Since the mass of the neutrino is very small, this ends up being a very small factor. Okay, and this interaction can be approximated by some point-like interaction, the delta function interaction in position space. So we end up getting, now I should mention there's a slight complication here in that the electron here and the daughter nucleus have a long-range Coulomb interaction between them, and so you cannot actually neglect the fact that these long-range Coulomb interactions have to be taken into account. It modifies the form of the asymptotic wave function. So if you do this properly, you find that you end up getting in this calculation this factor that's called the Fermi function, and this Fermi function is 2 pi eta 1 minus eta minus 2 pi eta. Okay, and where eta is the e squared c or h bar momentum of the electron. And so if you were to then measure the intensity of this decay, let's say for bismuth 210 versus the kinetic energy of the electrons, then you see some pattern like this. Now, if you look very, very carefully, we're talking about the fact that you can see a small dependence on the neutrino mass, or actually the anti-neutrino mass, but that's the same as the neutrino. The mass of the antiparticle is the same as the mass of the particle. And so you can actually, in principle, measure the mass of the neutrino if you could detect this process here. But this only happens really close to the point where the electron has the maximum kinetic energy. So where you're maximizing this denominator here, where the total energy is close to the energy of the electron here. And so that's in this region here. So if you were to measure if you were to look very carefully at this region here, you could see a difference between having a neutrino with mass 0, massless neutrino, or having a mass of 1 eV. And that's actually the focus of an ongoing experiment right now, CAPTRINE, which is the Karlsruhe tritium neutrino experiment. And so what they do is they look at the decay of tritium. So tritium is just an isotope of hydrogen, 2 neutrons and a proton, and it decays with a half-life of 12 years. And so it decays into helium-3, and you have an electron and anti-electron neutrino. So what they have is this huge spectrometer where they have a bunch of tritium in here. It's very hard to do this experiment, very expensive. And they just wait for this tritium to decay. It decays, well, if you have enough of it, then you can make these, you get a rather nice signal. And they've just, they've done this measurement, and they can get a rough bound on the mass of the neutrino. There was actually a colloquium last year by Timothy Chup, I believe, where he talked about the latest results from Karlsruhe, from CAPTRINE. This experiment is actually, there's a fun story associated with this experiment, in that Karlsruhe is a town in Germany, And it's what's funny is that they this spectrometer, which is huge, was actually built only maybe 300 kilometers away from Karlsruhe, but they had to they couldn't actually, because it was so wide it couldn't go on the roads. It was just too big. It simply wouldn't work. They couldn't put it on the railway either. It was too wide. So they actually used the rivers to transport this guy. And they, instead of just going maybe 300 kilometers, they had to go 9,000 kilometers around like this by sea and by rivers. And then the very last part of it, my understanding is that they actually had to pass through this village where they just barely passed through. Of course, they measured all these things, but they barely passed through this passageway between these two houses, which is kind of a fun story. So that's all I had for today. We'll continue on next time, and we'll talk about beta decay rates and what are called these FT values, okay, involving the Fermi function. And I'll see you guys next time.